For over a century, general relativity has painted a strange, often unintuitive picture of our universe. It bends, it warps, it curves under the weight of mass and energy. And in those curves, something even stranger might exist, a wormhole, a hypothetical bridge between distant regions of spacetime. Wormholes are solutions to Einstein's field equations, the same equations that predict black holes, gravitational waves, and the expansion of the universe. The first serious mathematical description came from Einstein and Nathan Rosen in 1935. They described what's now called the Einstein-Rosen bridge, a solution connecting two black holes. But this bridge wasn't traversable. In fact, it would pinch off faster than light could cross it, making it essentially useless for travel. The idea was revived in the 1980s when the possibility of traversable wormholes was explored. Stable, non-singular tunnels that, at least in principle, a spaceship could pass through. But could exotic matter, with negative energy density, hold a wormhole open long enough to use it? To keep a wormhole from collapsing, you'd need matter that violates the null energy condition, a foundational assumption in most classical physics. It would need to exert negative pressure, pushing outward against gravitational collapse. The Casimir effect shows that in a vacuum between two conducting plates, negative energy densities can arise due to vacuum fluctuations. The amount of negative energy needed to stabilize a macroscopic wormhole would be enormous, possibly greater than the mass energy of a star. And more importantly, we don't know how to contain or manipulate negative energy fields without catastrophic side effects. Wormholes may also be unstable due to quantum fluctuations. Even tiny disturbances might trigger a feedback loop that destroys the structure. Traversable wormholes might not just connect space, they could connect time. If one mouth is accelerated near light speed, special relativity tells us that time dilation kicks in. Bring the two mouths back together, and suddenly you've got a time machine. This raises deep issues with causality. The chronology protection conjecture proposed by Stephen Hawking suggests that the laws of physics may prevent time travel, not just for narrative consistency, but due to quantum instabilities that would destroy a time machine the moment it could create a paradox. We don't yet have a complete theory of quantum gravity, but speculative ideas suggest wormholes might not just be allowed, they might be inevitable. The EPR conjecture, proposed by Leonard Susskind and Juan Maldacena, suggests that entangled particles may be connected by tiny, non-traversable wormholes, hinting that space-time connectivity and quantum entanglement could be two sides of the same coin. Some solutions in string theory allow for wormhole-like structures, though usually in higher dimensional spaces or idealized universes. Then there's loop quantum gravity, where space-time itself is quantized, potentially allowing for topological defects or shortcuts. But until we unify quantum mechanics with general relativity, wormholes remain in the borderlands of theory. So, will we ever use wormholes to travel? Who knows? But what we do know is they are windows into the edge of human knowledge and the vast territory that lies beyond.